Okay.
All my classmates were young. Thank you.
I think my presentation is fairly concise. It's like what's presented, but it's just a matter of, you know.
Sweaty. Oh, I'm sorry. Oh, wow.
You need some energy, right?
Oh, yeah.
Hi, Hoang. Thanks for coming.
Yep. Good to see you again.
Yeah, pleasure, man. Please take some coffee.
Oh my goodness.
Yeah, I got lots of gifts.
Yeah. What one do you want? Okay, wait. Thank you. It just says there's 4 different cases.
Thank you.
Okay, well, it looks like blackberry, blueberry, vanilla, apple. What do you want?
I'm fine with
Okay, I want that one then. Jeez. Okay.
Look at this.
Was my project not good enough to make the first page? Mine's not on there either.
There will be second edition, so if you have some
Corrections
corrections or complaints, you can match them.
That's so good.
Вот вы самого крепкого орешка послушаете.
We got to talk to you. Be careful. Oh, I didn't know you were going to be here. Yeah, I mean, he sent me a message today.
That's going to be tough time for students now, huh?
And I'm in the building. That's not right.
Yeah.
Try to talk to some people.
That's good.
Yeah.
I was like halfway between. I kind of would. Yeah.
Oh,
I should have done that, but I didn't. So you look great.
They want to wait until they call you.
Pencil.
It's beautiful. I'm so happy I have this.
It's, you know, it's small.
Way too fast. Let them wait.
Just one small step.
Huh?
Oh my gosh, I'm actually beautiful.
Oh wait, I'm not. Oh, okay.
What? No, I think you meant this.
Wait. Oh, that's not.
Oh, really? I think you might be.
Actually, yeah.
So the plan is after all presenters will come here, we'll do a little group photo and then start formal thing.
Perfect.
The plan is that
Hello, you as well. Good. So you got the computational experience.
I don't know if it's allowed, but
That's going to be good enough.
You guys want to be talking about?
we have another one,
Do you guys have this from him every week?
almost. I know. I just wait. Oh my gosh. Young silence. What?
So.
I think so. See, all I need is this, and then I can do like that.
No, this is whoever goes first. The second you fill it out.
When you turn this one,
Probably.
get rid of that unless you put that one. Offense, maybe. Significant there. Somewhat. Somewhat. Took me 5 minutes. Thank you.
All right.
Oh, thanks for coming.
This makes sense.
That's why they come if they want to see snow. I've seen snow for several years. And they don't get it, but it's snow.
I didn't know. I didn't. I can't read it.
That's true.
Oh, they sold it? Oh, they sold it. All right.
I do not know.
Other way.
There you go.
So we're missing Morgen and Steven. Well, we have first 2 speakers. We can probably start without them.
What order are we going in?
Huh?
Are we going in?
We are going in that order, and before we start, we'll do a group photo because maybe.
order.
No. It is, we need to put something here in the second edition. And if they're missing to come, we'll I put them by Photoshop.
Just for the message. And I didn't end Now I understand some things like
Before we start, let's just go and make group photo. And the attendees and guests are also welcome to participate in the photograph.
Oh, look it, we got the last one.
Maybe a couple of seats so that we
Oh, okay. Well, Morgan should probably sit because he has the tallest one. Where's his head zooming out? Yeah, that's true.
Okay. And maybe take the stuff as a.
Yeah, really, you're to the center. You're sitting.
Yeah, please do. Everyone is welcome to join the photo. It will show that it was very high attendance event. And if you decline to be on the photo, please.
That's okay. Well, they got this. 3 is enough.
Yeah, we're good.
You may not want to have that project, project something.
Oh, should we move like
Go
this
ahead.
way?
Maybe move a little bit
Oh.
to the.
Or there's a way to mute them.
Then he has it, so it doesn't work.
Give a little bit to your side. To
No, 'cause
Oh, there we go.
Okay.
Thank you.
Okay. Thank you very much.
I guess one.
Okay, so welcome to the last meeting of the CHEM364 meeting. By the end of semester, I finally learned the numbers. So the goal of the class was to get basic principles that allow to interpret and predict outcomes of measurements in physical chemistry characterization of materials at the basic level, and it went through getting basic concepts of quantum theory. In addition to this activity, attendees of the course were very brave and almost voluntarily decided to apply their skills to problems that are very outside of the course area, to practice their principles on something unbiased. And the presentations today were completed in time away from the class, in the labs or at home, and there will be 7 presentations, I hope, arranged by the subjects. So there will be chemical reactions, there will be a couple of dynamics of both electronic and nuclear degrees of freedom, there will be all the electronic degrees of freedom for electron transport interfaces, and there will be several talks on the phenomena related either to spin or magnetism. If you never seen Microsoft Windows and PowerPoint, here they are. And the talks are placed on the desktop according to the order, first, second, third. So when it is your turn, please come forward, click on your name and number, and start presenting. Ideally, it would be great if all talks are limited within 5 minutes, leaving about 3 minutes for questions. It always gets a little longer, but we shouldn't override this time because some of the class attendees need to have plans and other exams. So with this, I would like to invite the first speaker, Eungyo Hong, who will tell a story about... I want to give acknowledgement to tech support, to Daniel Erickson for this video conferencing, for NDSU for MATLAB licenses, and for all colleagues who are coming, for two postdoc, Dr. Eungyo Hong and Dr. Fatima, PhD candidate Aaron Ford, who are assisting in the projects, and to all visitors for supporting this event. So with this, the first talk of Eungyo Hong is starting. Thank you.
Hello everyone, my name is Eungyo Hong, and my final project was about the fragmentation of lanthanum cyclopentadienol, which is the organic metallic molecules. My specific goal was to figure out the activation energy of the first barrier of the reaction pathway and understanding the pain result with wave packet dynamics and Arrhenius law. The minimum activation energy that I obtained from the MATLAB code was P0, which is initial momentum is in 60 atomic units. The methodology I used in the MATLAB codes were Hamiltonian evolution operation and propagation of the Gaussian wave packet, as described in the slides. It was able to observe the theoretical relationship between the initial momentum and the temperature, that the initial momentum was proportional to the square root of the temperature. One of the most important things done in the class was interpreting the data with Arrhenius law. The Arrhenius law shows the linearized relationship between the rate of reaction and the square root, then the 1 over temperature. As you can see, the natural log of the natural log of the rate of reaction and 1/T make proportional relationship in the chemical reaction that it was tested and the equation is applied to our reaction as well. After plotting the graph, we could see that the graph is linear and check the Arrhenius law would apply to my reaction as well. And from the Arrhenius plot, we can derive the activation energy of the reaction mathematically. We can see the slope of the plot of negative activation energy over R. If we multiply R to the slope, the activation energy can be derived in the unit of the electron volt. And the remaining activation energy of the reaction is 0.474 electron volt. To summarize, it was able to observe the activation energy of the fragmentation of LACP, which is the molecule of my interest, and also was able to see the reaction fit into Arrhenius law. Thank you.
Let's end the speaker. And the presentation is open for discussion and questions.
So the barrier is 1EB or 1EV? What is EV?
It's probably a typo. It's EV, right?
Yeah.
All right. So the electron volt, right? So
Yeah.
EV doesn't mean anything.
More questions? I do have one. Proof. So you are fitting your numerical results for reaction rate.
Yeah.
Where do you get these rates? Where are they coming from?
They came from the MATLAB code.
No. You are considered an author of this code, and you should explain the principles. So, where the rates of reaction come from?
What physical
The
parameters?
rate of reaction comes from the slope of the MATLAB code from the MATLAB code obtained. So yeah.
Slope of
Yeah.
what?
What is your y and x?
The x is the time, and the y is the product, the possibility of the product obtained.
Excellent. This is correct. But where do you get probability of product? And you may refer to your equations or explain by words.
The probability of the product obtained is
Please show your equations. You may furnish. You may have shown it. No, yeah. Equations. Yeah, sure. So you're computing wave function.
Yeah, that's right.
As it goes in time. And how do you extract the probability of the product if you have a function at each time? And any of class attendees are welcome to contribute.
I think right now I can't.
No, you can. You can.
I can't.
You do. You can. So please show your dynamics.
Yeah.
Okay. So what is moving?
Oh, the moving is the wave packet of the initial molecule.
But wave packet, what is it? Is it wave function or probability distribution?
The wave function itself.
But wave function can be negative, and your thing is always positive.
Probability distribution.
Okay. And when it moves forth and back.
Yeah.
So right now, is it open ring or closed ring?
The starting point is the open ring, and the end point is the closed ring, because it's the back reaction, and the forward reaction is the opening reaction of the closed ring.
So how does position of the wave packet relates to probability of a ring being open or closed?
Greater the probability.
Where? In which spatial region? just show on your display.
So your question is the probability of the open ring?
Yes, probability of the closed ring.
This point is greater at this point.
But it is not point; it is a range. Range.
Yeah. Which range?
Yes, which range corresponds to open and closed?
This range is corresponding to the string, and this is corresponding.
So you need to integrate your probability distribution over the range, and it will be probability of your product. Right?
Yeah.
It is what you wanted to say. Yeah. Okay, let's thank Eungyo for nice answers. And with the next presentation will be by Alyssa Roberts. She was extremely brave to take a problem which is at least twice more complicated than the previous one. In addition to nuclear degrees of freedom, she does have electronic degrees of freedom which are entangled. And the problem that she's going to explain was a major part of the Nobel Prize award to Dr. Ahmedzived. So, the floor is yours.
Okay, so my project was the photolysis of methyl iodide, otherwise known as iodomethane. So why investigate methyl iodide in the first place? So in organic chemistry, it is known to be the carbon of the methyl iodide is susceptible to a nucleophilic attack, and iodine is also a strong leaving group, so it's really easy to methylate products using this molecule. And then also, it's very small, so it's slightly easier to demonstrate in, MATLAB. So the products are easier to interpret than a triatomic model. So ethane, ethyl iodide would be significantly more complicated than methyl iodide. So that's part of the reason why we chose this. So what my simulations model is pump probe spectroscopy. So it's a 1 femtosecond pulse that splits into two sub-pulses. One pulse is the pump, which excites the electron, and the other one is the probe, which detects it. And then, so the pulse is significantly shorter than the relaxation of it. So you can excite the electron without having it interfere with the relaxation of the electron. So that is also the reason we investigate it. And different things that you can change are that the configuration the configurations that you can change are the amplitude, the phase, the polarization, and the frequency. So those are just things that you can tweak to make it exactly the way you want to detect it. So after it excites, it relaxes into two different spin states. So the spin 1/2 and the spin 3/4. Spin 1/2 has a higher energy than the spin 3/4 does. And in literature, they're denoted as the I stars, the spin 1/2, and then the regular I is the spin 3/2. And so the higher energy is seen here, and these are just the labels for the potential energy surfaces that we investigated. And this is the reaction barrier for just the breaking of the methyl iodide. So I'm not going to get into methodology, but it's all here. Okay, well, this is the initial wave function. So it has a few different components to it. So I don't know how in depth to go, but we have the Hamiltonian, the actual equation for the initial wave function, the potential energy surface calculations, as well as how I converted the temperature in relation to momentum. So here are my videos, that's the word. So this is the excited electron, and the electron is relaxing. This red here is the overall probability of the electron to be in the two different potential energy surfaces. And then these little humps here are the wave packets propagating as a function of the bond between the iodine and the carbon. So as you can see, and this is temperature 0 with a momentum of 0. So as you can see, as it propagates, the bottom one, which is the spin 3/2, propagates significantly faster than the one on the top.
Again, it's too many lines on this graph. So you have 3 different types of potential. So what is it? The
Yeah.
green lines. I mean, green lines, which looks like a potential.
Yeah, there's two different. There's a okay, so it's a so there's these two here are relaxed to the same state, whereas there's only one state here. And off the top of my head, I can't tell you. There's but it's in my report. I can't remember right now though. There's different ways to get to that state. So there's I think it's I can tell you, but it relaxes into two different states. So this state and this state, they both relax in the same way.
But where's your potential?
Can you show it on equations? In your slide with equations, there are potentials like V of x.
Are you talking about this?
Yes. Can you explain what's the difference between V sub 0, V sub 1, V sub 2, V sub 3?
Oh, so this is three lines based on these terms of four.
Can you just briefly comment what's the difference of this V naught, V1, V2, V3, and how it relates to the question of Professor Kilina?
Wouldn't it be the well depth? So the variations in the well depth would be what causes it to relax differently. I mean, that's...
Yes, but you may highlight that there are 4 different potentials.
Oh, well, yeah, here.
And those 4 different potentials is what you are showing.
Yeah. Yeah, well, yeah.
But what's the difference between them? Why do you need 4 different potentials?
Because they relax in different manners. There's one that's like a horizontal, I think that's what it's called, at transition. And then there's one that's, I can't remember. It would really help if I could remember the word right now. But there's different types of relaxation. So there's one that...
you mean conservative and dissociated? Or something different?
No, it's sure, I can't remember it. But it relaxes in different manners. So there's just the 3 different lines, and then they end up at different spin states.
Mm-hmm.
So different products that are similar in energy?
Yeah, basically. So 2 of them result in the same energy, and then one of them results in a different one. So there's 3 lines. The 4th line, I'm not sure what you're talking about. This is the electron. These are the 2 probabilities. So the black and the green are the probabilities. This is the overall distribution, and these are the 3 lines that we're talking about. This is the non-excited state. I guess so. There's no, since it's excited, there's no electrons on this non-probability. Yeah. Okay. Well, we'll continue. So the second one is a temperature of negative 194 degrees Celsius. So the initial P0 that I chose was 10. And so as you can see, it's starting to get a little bit closer for the distribution as it's propagating. They start to get similar and similar. I'm not going to let this go to the end because we have a time limit. So as the temperature increases, they become more and more similar, basically mimicking each other, but the distribution remains the same. And I thought that was weird, so we investigated it further. So this time up here is a little off, so it's actually going from 0 to further rather than from negative to nothing, because it was simulated differently previously. So if we let the temperature oscillate the molecule beforehand, when it eventually will excite, the probability distribution will vary differently than it did at the same temperature previously. So yeah, this one's a little bit longer. So this is the same simulation, except for this one was isolating previously. So you can see that it's very different looking than it was here, where this one had nice lines. This one has very different, oscillating features to it, and they propagate at roughly the similar time, but still a little different. So if I were to do this further, I would allow it to oscillate previous to the excitation to allow it to actually simulate the molecule correctly. So, anyways, my conclusions were temperature increases the rate at which the I star state propagates, and then the propagation ratio varies if it's allowed to oscillate before it's excited. So that's it.
Okay, let's thank Alyssa. So, any questions?
Can you explain your other two terms in your Hamiltonian? Off diagonal one? And how did you choose the coefficients on those elements? Parameters?
Okay, so well, I did not choose it. That's I think something that remained constant between all of them. No, I cannot. I'm sorry.
Let's skip values of this constants and discuss just the operator part with this ket and brat. In green and in your blue highlighted things, the bra and ket terms have different indices. What does it symbolize?
Oh, it's the transition between the initial energy state and the excited energy state. So just the energy transition between the two of them.
Mm-hmm.
And then the other one is the relaxation.
Or is transition between what?
3 and 2?
Yeah.
Yeah.
Britain? Partially satisfied? Okay.
So can you return back to your movie? So for the, I guess, my understanding is that at higher temperatures, which means this other, on the
one on
left side, right? So you excite to the highest parabola, or not parabola, whatever it is.
So in all of them, they're excited to the same point. And between these two, you can see that they're excited.
But you start your initial, right? Packet starts in the highest potential.
Yes.
Then it reaches a point where the both green lines coincide.
Are you talking about like this point right here?
Yeah, or it goes slow for the second case, doesn't matter, right?
Yeah.
So, and then what happens with the packet after it's reaching this crossing point? Because, I mean, movie was...
So it splits, basically.
Mm-hmm.
Splits?
Yeah.
Is it splits like 50%, or you have
I did not
more
do the
there, more there, and
integrations,
how
but
it changes with
visually,
temperature?
It does look like it's, that's like why I, visually it does look like it's about 50-50.
Mm-hmm.
I did not do the integrations for it, but just looking at it, it does. That's why we did the, I was confused on that. That's why we did this one here. Which is
And this is for higher temperature, right?
Yeah, it's not exactly the same, but it coincides with this one. So by oscillating it in the beginning, the ratios change, and that's why we did the, like letting it feel the temperature.
Yeah, so if you change the conditions, then the splitting of the packet goes
Yes.
with, so more goes down and less
More
stays
goes
on the
up.
higher.
Because of the
Oh, more goes up?
Yeah, more goes up because of the higher energy available.
Okay. Oh, yeah, temperature. Okay.
Yeah. So, I mean, it still looks approximately equal, and I'd have to do the integrations to tell, but it definitely does look like there's a significant more on the upper range than there was previously. It's just distributed.
Interesting. Thanks.
So you can control outcome of chemical reaction. Okay.
Just pushing a button.
Professor
So a
Hoang.
quick question. So in your simulation, the temperature goes from minus 200 centigrade to 41 or something.
Yeah.
What is the typical temperature in this town?
I think it would just depend on whatever you're doing it in. I think that they do it more like colder. I think it's frozen when you excite it. I'm not 100% sure on that, like just experimentally wise. But I would assume that it's not above room temperature, that they would probably have to like have some sort of stabilization factor, so it'd probably be pretty cold. So.
If you're not sure, I would guess what was to say liquid nitrogen.
Liquid nitrogen, so what's that, negative 70? Negative
Nitrogen or helium?
Nitrogen is less
It would be
expensive.
less than 0, I'm assuming.
It's good to know,
Yeah.
because whatever, we can throw in whatever number for a computer to do, right? But
Yeah.
you have to think about whether it's relevant to experiments or not. So, yeah.
More questions to Alyssa? If not, I thank her once again.
Question for Dmitri. What is the scale for this grade?
If you have your opinion about
That's
performance,
not like going from 1 to 10?
it goes.
Or should we just put A, B, C, D?
Yes, it goes alphabetically, like same as grades, A, B, C, D.
Okay.
Just put A everywhere.
I tried.
So Morgen Hagerott will present another implementation of the same philosophy when the electronic and nuclear degrees of freedom are entangled, and he will try to identify similar features in quantum dots.
All right, so as Dmitri said, I'll be doing my final presentation on Polaron states for infrared emission in perovskite quantum dot. So first, just like a real quick overview of quantum dots. They're nanoparticles of semiconductors, and they have these special properties due to their small size, and with this allows the transfer of electrons, which makes all this possible with the light emission when they're excited. And then a couple applications. A huge application for this right now is TVs. Samsung makes a QLED TV that uses this technology, which allows them to get these very nice colors with deep contrast. Another application with the perovskite quantum dots in particular is solar panels, which is becoming a more used technology due to their high conductivity. So some of the important equations in this project here, obviously the Hamiltonian, and there's a couple different stages of that, as well as the evolution operator, which allows us to kind of see where these things are going to be going, and then a few other parameters here, and the Arrhenius equation, same as Eungyo's, looking at activation energy. So there's a few different videos here. The first one is at a lower P0, which is the initial momentum of this curve. It goes from the blue curve, which is the excited state, down to the ground state, which is the red curve. And it is seen that the vibration is a lot higher in the ground state as compared to the excited state. It kind of goes slow, but
Okay, slow is good.
and then this is another one at a much higher initial momentum. And so this one ends up moving a lot quicker. And as you see in this one, the ground state is taking a lot longer to fluctuate. It's got a lot less vibrational energy because of this higher initial momentum. There we go. And then, so for some data collection, the way that it was done is to determine the rate rather than being able to use the rate that came out of the code. It is seen here that it's averaging this this overall rate, whereas it has to just be done y over x and calculating the rate that way because of the drop off at the other end. That data is not good for the collection. It throws out the average. And with this, the Arrhenius plot was made using the 1 over temperature along with the rates that were gathered. And within this collection of data points, there was, on the two extremes, a lot of discrepancy in the data, whereas in the middle, it leveled off and formed a nicer curve in which this plot was taken from. And here, from here, the slope is where we get our activation energy from. Any questions?
Well, let's thank Morgen for the presentation. And paper is open for discussion and questions.
On your slide that had the wave packet moving, you gave it initial momentums of about E50. Do those have units?
Yeah, it's just the atomic units.
2. They're satisfied. More questions?
I didn't realize how exactly Well, you're showing actually two-level system, electronic system, which is coupled to the vibrational mode, kind of synchronic, right? And you just consider the evolution of your wave packet going from one electronic state to another through the kind of vibronic levels. How is it related to the perovskite?
So it's kind of simulating as the perovskite is excited through, in this case it was infrared emission. It's showing that as this electron is added, it's the shortening and lengthening of the bonds that creates this jump of energy.
But can I say that, for example, lect44 is also has a you can excite it at the in really like in the infrared range because it's very narrow band gap semiconductor. Then all the story can be applied to the lect44 crystal. Right? Like actually, it's not really perovskites. It's any kind of semiconductor crystal with a small band gap where the excitation, right, is in the infrared range or maybe near infrared range, right?
Yes.
And let me advocate or add to
or something really about perovskites.
The offset of blue and red along x-axis is bigger in perovskite materials because the bonds are softer. In more solid crystals, they will be almost overlapping.
So technically, you can make this offset of levels, and then say, well, I'm looking on a different relaxation rates in perovskites or perovskites with this type of anions like iodine, lead, or whatever, right? And this might be also kind of further parameters which you can play with.
Yeah.
Nice. Okay. Thanks.
I do have a question, and it is very challenging. Do not fear if you cannot answer. Just try your best. Show your erroneous plot. So when Eungyo was showing his erroneous plot, the slope was in the opposite direction, which means like with increase of temperature, rate was higher.
Yeah.
In your simulation, with increase of temperature, rate is getting slower. How do you interpret it, if you can?
Yeah, initially when I was getting that, I was really confused because I was seeing, when looking at other Arrhenius plots, and as well as Eungyo's, it going in that negative slope. And I was confused at first, but then as I was looking back through the data that I was getting in my Excel plot, I was seeing kind of the opposite of what is traditional, and it was showing that as the temperature increased, with as well as the P naught was increased, the rates were actually decreasing.
But
is it similar to what Alyssa was showing for her case?
No, the connection is no straightforward. But can you bring your potentials or anything which shows your two potentials, curves, parabolas?
Oh, the two. Right.
Yeah, for example, here. So how does blue parabola on the left, at which point of red parabola they intersect?
It intersects at the bottom portion of it.
Yes, and here I need to add, you answered everything correctly, but this corresponds to activation-less transition, which gives absolute maximum. And any changes to the system compared to this configuration, either increasing temperature or changing offsets, you only slow down the reaction. So this surprise is expected. Okay. More questions to Morgen? If no, let's thank him once again. And we are starting next chapter consisting of only one presentation, Kristen Patnode. Her research project will be different from everything before. Her reaction coordinate will be not position of ions, but position of electrons. And there will be no nuclear motion. It will be only electronic degree of freedom along coordinate. And she is applying to some photovoltaic interfaces. So it's yours?
Yeah, so as Dr. Kilin said, my name is Kristen Patnode, and I'll be presenting on charge transfer between a perovskite semiconductor and electron accepting titanium dioxide feed CHEMs. First here I just have an image for you guys of the three-dimensional perovskite and then the one-dimensional projection. I'll speak a little bit on how we got the three-dimensional image into a one-dimensional projection in just a second, but just to familiarize yourselves with what this perovskite looks like in the MATLAB produced plots. You'll be seeing this throughout the rest of the plots in my entire presentation. So in order to first get that 3D image into a one-dimensional projection, we had to collapse our three-dimensional potential into a one-dimensional potential. To do this, you apply a double integral in order to remove your two dimensions that we're not going to be using, and then we have normalization factor as well. Our potential is described with a relationship to our electric field, which is that capital E, which is going to be our main variable throughout, where that mu is just a constant. Our Hamiltonian is going to be used as well in order to calculate our evolution operator. And so that Hamiltonian is also dependent on our potential. So we're going to notice a dependence of our probability of finding the electron in a specific space is going to be dependent on our applied potential. That's because our evolution operator is dependent on that Hamiltonian, which is dependent on the potential. And so I just have a further explanation to outline or identify that each different potential is going to correspond to a different electric field, which is just important to note. And you'll notice that in the plots, we do see a direct relationship between our change in potential and our electric field. Furthermore, in order to get a rate to determine how our electron is moving in and out of the perovskite semiconductor, we choose an eigenstate and then run our code initially. And then from that, we're going to plot a graph that's going to show us the population of electrons in our actual accepting agent versus in the semiconductor as a function of time and the rate of population gain. And then in order to extract the rate from that, we'll do a derivative over time and convert that into a rate in picoseconds or inverse picoseconds. Here I have about 1 picosecond just to describe if you have an excited electron. You notice that at excitation orbitals about 7 to 9, the rate of transition from electron in the semiconductor to the TiO2 agent was about 1 inverse picosecond. It's predicted that at an without excitation of the electron, that rate will be close to 0. So here I have an image to demonstrate what happens when you have a non-excited electron versus an excited electron in the perovskite semiconductor. Without exciting the electron and without applying a field, there's not much movement in the electron. These are static images, I'll point that out right now. But once you excite that electron, we see it's almost impossible to predict where that electron would be, as the probability of it existing in any point of the semiconductor or the TiO2 agent is almost the same, and so it would be impossible to determine where it is in that system. So then to give a few videos of what this looks like when we have no applied field and our initial eigenstate at no excitation, we're going to see the electron move. And then when we excite the electron, not much is going to change in that motion. You'll see some differences in intensity, but it's unlikely that the electron is going to move in or out of that semiconductor. However, once we start to apply fields here, I have just a demonstration of potential versus, this is all those colored lines are eigenstates for each respective potential. Just to demonstrate what we're going to do, we're going to start at an initial eigenstate of a ground eigenstate, and then excite it up to about 7 or 9. And so in the middle is where we have no applied field, which is what we just looked at. And then we have both a negative and a positive field. And we're going to look at how those affect the electron's motion differently. So first, if you apply a positive field and you're at no excitation of the electron has a hard time moving outside of the semiconductor. To remind you, this middle section is our semiconductor, and then as we move this way, we get to our titanium dioxide accepting agent. Then once we excite the electron, here we've excited to a state of 9, we see a lot more motion of the electron, and it actually makes its way outside of the semiconductor and even starts to populate that accepting agent. So then just to remind you, we're moving on to then apply a negative field. And again, we're going to start at an initial ground state without exciting the electron. And then we'll excite the electron again to a state of about 9. And once again, we see that almost static electron inside the semiconductor. And then as we apply excitation, we notice the movement of the electron. And in this case, we actually saw even more motion towards the left side of the semiconductor, which I thought was interesting. That's just, that left side is not our accepting agent. So further research would have to be done into why that happens. Also, be interesting to do further work on optimizing photo excitation of the electron to see the most beneficial state of excitation to move that electron into your desired acceptor. And with that, I think that's
Okay, that's fine. And presentation is open for discussion.
I just have a conceptual question overall. So you kind of said that if you are in a ground state of in a perovskite area, right? So then your electron stays there forever, right? Is it really true?
Probably not forever.
Okay.
Likely.
What is kind of quantum processes we know should happen even if the barrier is high? If it's not infinitely large, then what happens with the electron?
Inevitably, it will move.
It will
widen out the
tunnel,
distance.
right? Tunnel through the barrier. But this process just goes very, very slow. The probability is very, very small, right? So that's why it's not like it's forever be there. It still probably will tunnel, but you probably need to wait weeks to see this something appearing at the other side of your barrier.
More questions? Okay, everyone is happy.
You said that when it goes, so you said that you apply negative and positive field, and you also said excitation, but you didn't mean light excitation. It was not excited with light.
Oh, sorry.
What kind of field, and what is negative, positive? I actually know the answer.
You probably do. For the applied field, they both applied actually by Dr.
What kind of field?
An electric field.
Okay.
Applied electric field to the conductor, semiconductor. But then within our code, we were able to excite the eigenstate conditions of the electron.
But what does it mean, positive or negative? So you apply either positive or negative voltage, in other words, right? Yes. But did you show what happens if you apply negative voltage?
That would be these videos here, and then the first set, these were positive voltage. I want to say it was 0.05 and negative 0.5.
Just verbally describe how
what's the difference?
potential changes for positive and negative voltage or positive negative field. Just verbally describe how the potential changes. One slide forward. Yes.
Because
and there are three potentials: this field and field of opposite signs. Can you just verbally describe what's the difference in this thick black curve?
Because they look very similar.
Yeah. So the primary difference that we see is actually on this left side. Shouldn't be a change to the titanium accepting agent. But
this is with which field? This is this field, right?
Yeah, so this example is with no field.
Okay.
And then when we apply, the negative field is on this side. Oh, I'm sorry. Negative field is on this side.
On that side is your titanium, right?
Yes, the titanium is all the way over.
And on that side is your dye?
Yes.
Okay, so then what happens with the potentials plus minus?
As the potential goes negative, our dye potential becomes a lot less defined and broader, whereas when we have a positive, it becomes more narrow and more noticeable.
Yeah, and for titanium, it's a backward behavior.
Yes.
So that's probably explains why you
notice
it goes either right or left.
Yeah.
Because you're really low in the barrier, either on the left side or the right side.
Huh. Can you go to your equation slide? It seems you were addressing the second equation. Yes. So your potential under electric field is getting constant slope, where mu is your position operator, right? So depending on the sign of the field, you get positive or negative additional component. Good.
Question. I'm wondering what are the parameters that go into the simulation. For example, for every semiconductor, let's say the band gap value is one of the values. So what you're showing, does it depend on, let's say, the band gap value of perovskite and titanium dioxide? Does it depend on any intrinsic properties of the material at all, or is this very general that can be applied to any material?
It's a good question. I didn't look into that in my.
Try your best and maybe point attention to the first equation on your slide.
The question is, can you apply this to a perovskite material with different components?
Or maybe not perovskite. What if you change your materials? Instead of perovskite, you use something different. Polymers. Conjugated polymers.
Since it's dependent on potential and not necessarily the intrinsic properties of your materials, I would.
But potential does depend or not depend on the intrinsic properties of materials.
So
the answer is
depend on your material. But you could likely.
And can you return back where you're showing how you go from 3D atomic structure?
It is here.
I mean, the image.
Okay.
Yeah, here, right? So
Right,
look.
yeah.
So who was making this plot? Actually, is it you? Did you simulate this structure, or you took it from somewhere?
Collaborator.
Provided by Dr. Hong.
By who?
Dr. Hong.
Oh, okay. And how he was doing it, do you know?
Did you ask him?
No.
But do you have an
Maybe
vision?
Can you explain how did you obtain this?
This is from first principle.
As a potential.
From mass.
Do you think everyone? I don't know. I'm sure not everyone knows what is what.
I don't know what it's like.
Well, you need to apply special code which allows you to calculate the.
Yes.
With some approximations, you actually need to calculate to solve the Schrödinger equation.
This is just the electrostatic potential, right? So let's say you calculate the electrostatic potential from this to this, and you project on a two-dimensional, and you use one-dimensional.
Yes. So it is first principle data.
Right. So this is this property is intrinsic to the property to the materials that you're talking about, right? If you instead of if you replace, let's say, perovskite with something else, the curve is going to be different.
Yes.
And then your final result is going to be different.
And if the molecule is different, then probably you also will have slightly different shape for the right side for the potential. Same for the of course, very strongly depends on the material.
All right.
More questions? Let's thank Kristen once again for extending the questions. And now we are starting the last chapter of 3 sections. So first will be presented by Amelia Anderson, and she will help us to recall principles of Bohr theory, which is behind atomic spectroscopy.
Yeah, so like you said, my name is Amelia, and I did my project on the 2D rotation of Bohr model for non-equilibrium orbitals. Some of the equations I used this first equation, which converts angular momentum to polar coordinates, so we could plot the angular momentum in a way that we can understand it on the Bohr model. And then the second equation is it shows the difference between kinetic and potential energies and how they're related to the Hamiltonian. My methods, I used a MATLAB code written by Dr. Kilin, and then I added the commands to automatically save the videos so I could upload those to YouTube later, so I can add them to my presentation. I changed the numbers of nodes and then reran the code so we can see how the nodes changes the angular momentum of the electron movement, and then we analyzed how those nodes affect the movement. So here is just a polar standing wave, and the red line on there, they're all kind of overlapping, but just imagine with me and we'll see them on later plots. The red line is the real part of the wave function, and the green line is the imaginary part. And then the blue line is the combination of those, which is the red line squared plus the green line squared and the absolute value of that. And then the blue line shows the stability of the electron in each node and orbital. So if the blue later in the videos, if the blue line is pretty much unmoving, then the electron is going to be more stable, and if it's moving, then the electron is not stable and will quickly change so it will become more stable, and then it's less likely to undergo a transfer to a different node. So here's the first node. I ran it with 1.56 nodes, and you can see the very quick movement of both the red, green, and the combination of the two in the blue line. So when there's not an even integer number of nodes, then the electron is a lot less stable, and it's going to try to get back to a more stable state. And then the second one, we did 2.02 nodes. So clearly those movements are a lot more stable, and the combination of the red and the blue the red and the green makes the blue line unmoving. So this electron is pretty stable in its condition. And then moving forward, here's 2.64 nodes. And this is unstable once again because it's not an even integer. And then finally, here's 3 nodes, 3.01 nodes. And this is stable once again. And that blue line is unmoving, so it's happy in its current position. And then, so conclusions for this project was as the number of nodes change, the radius from the nucleus increases as the number of nodes increase. If we go back and just compare the radius of each of these, it clearly gets larger as we move forward, and finally the largest at 3 nodes. And then, yeah, as I mentioned before, the even integer values create smoother movements and more stable atoms. And then the value of orbitals is 2 times the number of the nodes, so there's 1 positive and 1 negative for each node. And then finally, we looked at limitations of the Bohr model, so it's only a 2D model, so it can't show 3D movement, and that led to the lack of understanding of what the electron would do in a 3D space. There's some references in there.
Okay, thank you, Amelia. And the presentation is open for discussion.
So in your conclusions, you said that you need an integer number for the nodes, right?
Yes.
So in other words, you need to quantize your momentum, your angular momentum should be quantized,
yes.
Right? And this is very valid, of course, statement, which you proved. However, you didn't show the results with 300. You were showing 301, 2 point something.
Yes.
Was it is it an issue to get exactly the even number for your code? Or you just didn't show it to us? Because it's not interesting.
Well, there's that. But the code did not run as well with completely even integers. We wanted to have 3 significant figures in each value of the nodes. So we just ran it not completely equal, but we got it as close.
So in other words, there's some bug in your code which not allowing you to really get exactly integer number.
Yes.
So there's maybe some numerical errors which
yes.
results that you need kind of a little correction, and you cannot really get the exact even number.
Yes.
More questions, please.
So can we use this simple picture you got to understand any no observation in experiment? Yes, any simple experiment that some experimental data where we can use this picture to understand?
I mean, you could use it in a multitude of different experiments if you're able to. This is kind of atom by atom, not the complication of a molecule. So yeah, the blue line just, if it's stable, then the electron is going to be less likely to transfer. But if you're looking at an atom where the blue line is moving all over the place, then the electron is going to be more likely to transfer. And we just, well, I looked at it as...
Electron is more likely to transfer from the atom.
Yes. Or move to a state where it can be more stable within that atom.
But can you really give some example of the experimental evidence of something like that?
Is there a connection to
Some experimental evidence of the Bohr model.
I did not look into that.
Come on.
You can.
What exactly is the reason why Bohr created his model? There was very clear need from experimental side why he really started working on it. And how he proved that his model is right.
He looked at
Let's go to your questions. Maybe they will help you. Yeah. So your last equation, what does it tell?
At the values of even integers of nodes, the don't exactly know.
So what is H?
Hamiltonian.
And which observable, which dimension it corresponds to? Like momentum, position, or starts with letter E? Observable, eigenstate of Hamiltonian, but it can be kinetic or potential. Yes, good. So if you plug in the quantized values, or if you look that you have integer number of nodes, what will be the values of energy from this Hamiltonian equation?
Would you get different energies for different values of your quantized L? And how is it changing? If L grows,
and the Hamiltonian grows.
Energy. Yeah.
So
Energy grows. And because L is quantized, then what happens with energy? Like L cannot take something in between because then your atom is not stable. Then you really need to take all integer numbers for L, right? Then how does it affect the energy? Does energy continuously changing when you?
Or it takes only discrete values.
Discrete values which depends on this L, right? And now go back to experiment. How does the hydrogen, the spectrum of hydrogen atom looks like in the visible range?
It's very discrete values.
Actually, there are 4 discrete lines, right? And this was kind of a main puzzle. No one could explain before Bohr. Why is it discrete? Why is not kind of a distribution like you see from the black body radiation, which is just spreaded kind of distribution in over all energies, right? And this exactly explains if you have one single electron in a hydrogen atom moving from the ground state to the first equilibrium, first, second, and so on, excited states, right? Results on the discrete energies. If they go in a visible range, you really can see them just by eye. And this is the evidence of this model. It works. He was able to use this model and predict these energies, which then were compared with the hydrogen atom spectra, and they looked very nicely there. I'm not sure whether you were thinking about this experiment.
People propose a model for purpose. They was trying to understand something, and usually it comes from there. So that's why I wanted to see the connection.
Right. More questions? Morgan? No? It's not questions, it's applause. Okay. Well, thanks, Amelia. So we have 2 more presentations. Steven will be the next. And his presentation will be very much different from anything we heard before, and very much different from anything you may have heard in the previous years of this class. So instead of looking on either electronic or nuclear degrees of freedom, he will look onto spin degrees of freedom.
Hi, my name is StevenWestra, and as Dr. Kilin said, I'll be talking about spin degrees of freedom.
We cannot hear you.
Oh, sorry.
Talk a little bit
Do
louder.
you need to launch the presentation mode?
Oh, right. you can't tell, I'm a little nervous. All I've had to eat today is coffee.
So, as you can take, if you are not in the good mood to speak over.
Hello? Yeah. Can you all hear me now?
Yes.
Yep. So, my name is StevenWestra, and as Dr. Kilin said, I'll be talking about spin degrees of freedom in electrons, and specifically the free induction decay of electrons from magnetic moments in NMR. So first, we're going to have to cover some theory, since as he said, mine is very different from everyone else's. And that would be, what exactly is spin? And that is a very hard question. If it wasn't, I'd probably have no real problem with it. So it's an intrinsic property of electrons and other fundamental particles, which doesn't really tell us anything. It's more accurately, it's a form of angular momentum of a particle. Probably the analogy, it's a ball that's spinning, except it's not a ball and it's not spinning. So then what is it? Well, specifically, the spin number of an electron is the eigenvalue of a wave equation for the k number of states where the wave function is an eigenfunction of s hat z for the summation of k terms of s hat z k. That would be the basically the z value for a vector of magnetization, basically. So that allows us to see that they'd be represented by a sphere, basically. That would be a Bloch sphere. Well, what is a Bloch sphere? It's a geometric representation of a qubit where the poles of the sphere represent the 0 and 1 states. More usefully, it's a way of visualizing the magnetic vector of a spinning electron as it moves through a magnetic field. So we have our magnetic vector is equal to g summation of k of the sk of time t, where the sk is the combination of the x, y, and z components of the vector, which are controlled by these equations, which I will show later. So, now what is a spin echo? So as the magnetic moments of a group of electrons move around a Bloch sphere around the equator, that at one point in time they will synchronize and constructively combine their signals into one very large signal. Now, the exact time that this happens for an atom is unique to each atom and to each electronic environment, also how it's bonded for every single state that there can be. This is the principle behind how NMR spectroscopy can differentiate elements and atomic structure this way. And now we have a very, very messy graph. So what's happening on this graph is that all of our electrons in the magnetic moment, in the ensemble, start at the same level. The pulse, the half pi magnetic pulse that brings the electrons from the poles of the Bloch sphere onto the equator, which is represented by these two lines, at which point the varying individual frequencies that they move around the equator, which is dependent on their individual electronic environment, cause them to diverge into these various purple and yellow-orange lines until they reach the pi pulse, which flips them 180 degrees in the sphere. And as you can see, that changes the way, so that now instead of diverging away from one point on the sphere, they are now on the opposite side, converging towards a separate point on the opposite side, which is represented here and here. And so we have two identical signals, despite the fact that they are now in different places in time and space. And so a more useful visualization, if you can't really wrap your head around that, we have our electrons here at the top of the Bloch sphere, which are then moved to the equator by the 90 degree or half pi pulse, so that they are now in the xy plane of the sphere. They then proceed, the various electrons, since this is more than one, move in various ways around the sphere at different rates, and that's such they counteract and destructively combine to reduce the total of the signal that you would see. This is until the pi pulse is received by them, at which point they flip to the opposite side of where their positions were originally on the sphere, and they now begin to converge to a single point on the opposite side of the sphere. So, a nice thing I got from Wikipedia shows this in a smooth motion. And you see that at one point they converge on the opposite side and form a new signal, even though there shouldn't be any magnetization present. Now, what did I do exactly? Well, as the electrons move, they move at different rates. Specifically, it's called the disorder is the variance between each individual magnetic moment as it moves. So, stated earlier, they are defined by the summation of the x, y, and z coordinates, which are defined by various differential equations. The important variable in this is the plus or minus I delta omega k. They do so at different rates. The difference between those is defined by the delta omega k. So here are the two the two formulas that I used earlier in the formula to define the magnetic vector. And here we have the delta omega k components, which are the important factors. So in the MATLAB code, delta omega k is represented as a multiple of omega. As you can see here, the original was 0.015, where this can be x represents any value that would differentiate between the different speeds that they move. With x is starting at 0.01 in 0.025 increments up to 0.02. So what does that look like? So here we see the signal that you would receive on the Bloch sphere, where as they move around the equator at different rates, they destructively counteract each other's signal until they converge at a single point, and we see a sudden surge in signal on the opposite side. Now, graphed to link to the YouTube video that Dr. Kilin helped me put together, that I took that from. If we graph that, we see this sort of graph, where the orange and blue line combined represent the measured magnetic signal. Now, as you can see, as disorder increases, this is 0.01, 0.0125, 0.015, and increasing so on to 0.02, the width of the peak increasingly narrows the larger the disorder is between them. So this is very important, as the width of the peak is a limitation in the resolution ability of an NMR to distinguish different electronic states. So if we graph that as a combination of the area of the peak over the multiples of W, we see this very smooth sloping trend line as the disorder of the state of the magnetic moments increases. And it says T2. I'm sorry, I did not define what that is. T2 is the relaxation time, the time that it takes for an electron that's been put through a magnetic field and been brought to the XY plane to return to its initial sort of state after it's removed from the electronic field. This value is different for every element and is part of the way that spin echo is used as a way of determining the state of the atom. So what happens if we make the disorder really, really large, like 7 times as large as the original one that we started with? And something very interesting happens. The total area of the peak completely breaks down, and it loses all symmetry. There's no symmetrical large peaks on either side. And what I'd speculate about what's causing this at this point is that the disorder is so large between each individual magnetic moment that they aren't able to immediately constructively rephase into a single point. By the time the first ones are rephasing, the other electromagnetic moments are still far around the sphere, and by the time the last ones are rephasing, the first ones have already returned to their initial values. Questions?
Okay, but thanks, Steven.
That was almost 10 minutes.
And presentations open for discussion.
Yes.
You mentioned that this is kind of applicable to the NMR spectroscopy.
Yes.
But then you were also talking about, like initially, I think you said it several times, that you talk about spin of an electron. What is used in NMR? What kind of spin they use? Is it for electrons or for something different?
Might have confused some there. But the important part is that
it doesn't change the overall, how to say, physics and formulas which you were showing.
Algebraic processing.
In an atom, are there anything else which
spin
has spin,
electrons.
or it's only electrons which do have spin? What about protons?
all elementary particles and quarks have spin. However, in the nucleus of an atom, they are counteracting.
Is proton a fermion or not?
No.
A proton, a single proton.
Yes.
Proton is a fermion, right? But if you talk about nucleus, right, depends on whether you have even or odd numbers, and they might be not. So in NMR, it's the same idea, but my understanding is that they talk about the spin of the nucleus, spin of the protons.
So in your talk, you can replace only one letter if you want to speak about electrons. Instead of NMR,
EPR.
EPR, yes. More questions to Steven? If not, then thank you once again. Please leave it here. So the next presentation is by John Swanson. So his presentation will be also very unlike and similar to anything you heard before. In recent year or couple of years, there was an interest to so-called two-dimensional quantum materials, and John was brave enough to try to apply skills from the course for exotic materials. Are you in a mood to speak loud, or you need to?
I'd rather you speak loudly.
Okay.
Hello, my name is John Swanson. I will be presenting on the correlation between eigenstates as the magnetic field is changed. So getting into that, just brief overview, not that people don't know what superconductors are, but a superconductor is a material which can move electrons from one atom to the next with no resistance. And so this is often researched on low temperatures, bringing metals down to low temperatures. They can become superconductors in many cases. But one area of research that maybe isn't as looked into or known about is the application of magnetic fields to form superconductors in metals. Because I know metals oftentimes, when they're superconductors, give off magnetic fields, but inducing them with a magnetic field may have a similar result to bringing it to low temperatures, if we look into that a bit. So, some basic methods of research. There's a MATLAB code that was used to do this experimentation. I'll get a little bit into what was behind that. And so through this, we took the eigenstates that were found through this code, and they were converted to density of states across energy. And then that was used to determine if a superconductor could be formed based on how the density of states reacted. And so some equations that were helpful in doing this. This first equation relates the Hamiltonian to energy in the eigenstates. And a lot of these are really intertwined, so actually doing this computationally may be incredibly challenging, which is why a code was used, because I'm not sure I could do any of this by hand. Second one, equation right here, we found, use the energy found in the first equation, and using the first equation to find the density of states. And then moving past that, this equation is used alongside this once this is solved, and it can be plugged back in, as you can see here. And then this is just an equation for the Hamiltonian, with L sub z being angular momentum, V sub z being magnetic field, and both of these are actually in the momentum space and not in any position. Yes.
What is LU and HO?
Okay, so LU is the lowest unoccupied molecular orbital, highest occupied. And so for this one, lowest is calculated using positive, highest using negative. And so a little bit of a representation of this last code here. This cone is kind of what that equation looks like when mapped out, again in the momentum space. And this ky and kx are represented as px and py here. And so the top is the lowest unoccupied, bottom is the highest occupied corresponding to positive and negative. And then this over here is a material that this could be researched upon. So this is the model of layered bismuth telluride, and it's just one of the lattices of that. And so this is something that the experimentation done could be done upon. Okay, so for the actual data, at the bottom here, these are the eigenstates across energy that were found through the experimentation. And above each of these is a corresponding density of states that were found when converted. So these first three, this is throughout the slides I'll show. This is as the magnetic field increases. And these first three are pretty similar. As you can see, this is the density of states of the holes where there weren't electrons in the lattice, and then of the electrons found. And the dotted line you'll see is the combination of the two of those. So nothing really too interesting here. As the magnetic field was increased even more, it was started to see that there was a bit of a dip here, which started to grow, as you can see in that last one, almost forming a peak. And then finally, here we can see this is the strongest peak that was found through this experimentation. I'm sure it could be found stronger if you were to get to closer values, but this is what was found. And then it started to dip down. And so what was determined from seeing this peak in the density of states is that it is evidence for a superconductor. I believe you can look at Fermi's golden rule for showing that when the density of states increases at a specific energy so sharply, it could indicate that a superconductor is being formed. And so, again, it flattens out afterwards, but that is, as a magnetic field is increased, that is something that is known to happen for density of states. So that doesn't prove this is true, but it gives further evidence that this is reliable. And so this is just a video of all of those kind of mapped out, kind of what that would look like. Just for a little bit of a better visualization of the density of states over time. Okay, so some observations that could be made here again by Fermi's golden rule. We can claim that as density of states increase at one specific energy, that you could maybe see a superconductor being formed. And so further indication of this was found when looking at the eigenstates of the found through this experimentation. And so I'm not going to show all of them because there's a lot, but I picked a specific few. So when the B field is 0, I believe this is the first eigenstate and the third one, according to our graphs on an earlier slide. There's relatively little to see here, which indicates there's little motion. And so as we move up in the magnetic field, this should be negative 2.33 times 10 to the negative 5. There's a lot more fringes here, as seen by the second eigenstate and fifth one, so I believe these two are. And the fringes should indicate that there's further motion within these eigenstates. And that continues up to negative 4 times 10 to the negative 5. And this is at a much higher energy and a much lower energy. But as you can see, there's a lot of activity going on there, which further indicates that there is motion, which would lead you to believe that maybe a superconductor could be formed under these conditions.
A second. So
yeah.
This is just different eigenstates at the same magnetic field, right? You
No,
fix the
no.
strength, so you're changing it.
This is magnetic field is 0. This is increased to 2.33 times 10
Which is kind of optimal, where you really see the formation of
And then the largest peak was seen at this one. And so this is at a higher energy, but this is as the magnetic field is increased. This is just a couple of the eigenstates taken out of that. And so observations, again, I said, as the fringes increase, that leads us to believe that there's an increase in motion. And there are the eigenstates, and my units are not quite great, but they're there, can't change them. And so basically what I took out of this is upon induction of a magnetic field, it could lead us to believe that a superconductor could be formed under the right conditions, which I think is something that's very interesting. So thank you.
Questions? Yes.
Sorry, I'm one of the students in my question.
Oh no.
Well, you're ready to upload infinitely. Okay, Alyssa.
Can you go back to just keep going? I'll take this out. Okay, right here.
Yes.
So on the first one that you have, why are the states less quantized as we keep going up? There's like obviously not like plateaus. Do you know like why it gets so weird? Or,
Like you mean with
nope, the bottom graph.
here?
Yeah.
Oh yeah, because they're not. So this dip. I know I looked into it at some point. I think it indicates a change in the motion, if I'm not mistaken. But I'm not entirely sure why it goes from, the tiers to that kind of steadily increasing pattern. I guess they're just because the eigenstates are probably taking from different spots that aren't necessarily in one plane, because the eigenstates are kind of correlating to this conic shape. But I could be mistaken in that.
Great question, and answer is almost complete. Can you indicate our attention to magnetic field equals 0? And count how many degenerate eigenstates you see if you start from lowest.
Here?
Yeah, no degeneracy for the lowest. And next one, how many? How many? How many? 4.
4. Yes.
Okay, now let's go to your eigenstates at the very end.
I mean here.
Eigenstates, not.
Oh, I see what you mean.
Yeah. So, can you explain how this degeneracy 1 and 4 relate to your eigenstates with 0 field?
So this is at 0 energy.
0 magnetic field.
Zero magnetic field. And so at the degeneracy of 1 and 4, you can see that both of these are, well, they're basically the same, at least in this, which indicates that both state there's little interaction, but not exactly sure that's what you're getting at.
Does momentum, he's on the right way. We will complete this thought, and thank you much, Alyssa, for great question. Is momentum changing or conserved in absence of magnetic field?
It appears to be
conserved. So if you create a state with very certain value of momentum, delta function of momentum, is there any mechanism to disturb it?
No.
No. So on your grid points for different values of momentum, please keep this eigen. On any value of grid point, the delta function certifying very specific value of momentum will be an eigenstate because there are no reasons to change eigenstate. Right? And if you take square lattice grid points, how many nearest neighbors are close to 0.0? You already answered, but let's focus on the back. This is 0 point. How many closest neighbors to this point along this grid lines? 1, 2, 3, 4. And all of them will have the same value of energy. Because it is proportional to the value of energy. So it's 4 degenerate. And it will be spiked from state with 1, degeneracy 1, and degeneracy. Can you go back to your degeneracy images with magnetic field 0? And can you maybe, can you now repeat the same to Alyssa and pointing right things on the.
I can do my best. So here, momentum is conserved as we go across. And so the closest 4 are seen up here to What was your question? Your question was more based
your question was why it's so smooth.
Yeah,
for the
on this
first,
one. Rather than
Well, and then it goes
this.
back to being like when it goes back to peak, it goes back to being normal again. I guess I was just wondering if there's like
a reason why it goes from. I get exactly what you're asking. Why it goes from the tiers to kind of a more curved pattern and then back to the tiers again.
Because of the discrete nature of grid points.
Okay.
So it could be a numerical artifact. If we take finer grid points, it may disappear. More.
Yes.
Can you get back to the slide with a picture of bismuth telluride?
Yes, for sure.
So bismuth telluride is a narrow bandgap semiconductor. Bandgap is about 0.1 something. So on the left, you show something which is more like metal, more like graphene. I don't see any bandgap. So do you think that your model on the left can be applicable to the material on the right?
I think a similar model might be, but maybe not this specific one. This was more of an example of something that has been used with superconductors that this may be able to be applied for, because I know this has been used to insulate in quantum computers with just some research that has recently been done. But I'm not sure if this exact model would be applicable to this.
I mean, the whole idea is you can use magnetic field to manipulate the electronic state near the bandgap, in the bandgap region. So, okay, then that's it. Okay, my question is very simple. Do you know of any example of real material where they observe, superconductivity by applying the magnetic field?
In my research, I could not find anywhere that this was observed in any material, but this was more just to show that maybe it could be found to be applied to some material, but I could not find any evidence of a material that has been shown to have that functionality yet.
Have you seen an opposite effect when increase of magnetic field limits the conductivity? Like your regime when you keep increasing it to higher values?
Well, eventually, like if you look here, as the magnetic field is continually increased, eventually it does start to
it lowers the conductivity.
lower the conductivity.
This is very standard effect observed in experiment. So half of these results agree with experiment.
Okay, that's good enough.
The other half is more the part that would be interesting to put further research into based on this evidence.
I don't know, something to keep in mind is, when you had the enhancement of the electronic state at the Fermi level, it may lead to superconductivity. But yes, it doesn't mean that if you had enhancement, yeah, you have to have the conductivity. Right? You may have it.
Yes.
Okay. Yeah.
It's necessary but not sufficient.
Yeah, right.
More questions to John?
I have a general question which is kind of related, or I would say the answer to my question was already answered in a question from Hoang. And so technically this bismuth telluride, right? So it's referred to the so-called Dirac materials because it's not small semiconductor, it's a Dirac materials, means they completely close the gap at one point, right? And what other materials do you know which behave in the same way?
Well, that's a wonderful question.
And anyone from audience may help to answer this question if it takes longer time.
I do not know of any names directly.
You should.
I should.
This is very common material. I would be very surprised if you have never seen it.
Because I know graphene works.
Yeah, this is one. This is the most common one, right? So, but there are of course more than one material like that. And technically, the computational chemistry was applied to create some kind of a predictions or database. They tried to go through many variations of possible semiconductors of multiple combinations, metal, non-metals, and calculating electronic structure, the dependence energy on the band, on a on the key points and checking whether you can get direct materials or not. And yeah, we found about hundreds of materials as predicted. Some of them not synthesized yet.
More questions to John? If no, please join me in and last note that probably all visitors will agree that it was a successful presentation. Please submit if you did this form, and class attendees can also do this. So the exposure of class attendees to unbiased problems was a chance to practice your knowledge in more real-life environment, and there is a hope that it will help to keep part of the knowledge more long-lasting in your memories, and it will eventually help in in other classes, like inorganic, Chem2, computational chemistry, which all you are invited to take, and in your academic teaching or industrial careers. With this, let me thank all speakers and participants of the discussion. Yes.
So may I just make a comment, because I was coming for Dmitri is teaching this course for about four times already, right? For 3. Anyway, I was coming for this presentation of students from previous years, at least 4, I think it was 4 times already. And I really was amazed with your presentations as a group, because usually, yeah, there are of course good presentations, very good presentations, but there are really presentations which are kind of very weak and very, people don't know what they do, we don't know how to ask questions. I was very, very pleased to see that all, how many, 8 people who were presenting really showing very, very good understanding, level of understanding was very high, and overall presentations were just interesting to listen to you. It was interesting to see what you were doing. So really, I think as a group, every of you was really, I don't know, I'm very excited seeing your presentations. Really great work, guys.
Okay. And with this, meeting is dismissed, and class is complete.
So I think, because I said that I fully agree with Svetlana. I'm really impressed with you guys' presentation skills. It's much better than the other events that I expected. Yeah, be proud of yourself. Yeah, lots of improvement.
We are proud of you, for sure.
Yeah, great job. Yeah.
Dr. Kilin, you have some.
I use it even as comments like it's fancy, but I usually keep it off because for whatever reason, like it builds up steam and it like drips out the side. Like, yeah, so it's like expands. So you walk in the class, it's like it's got like hot coffee.
7 of us? 7 of us?
What are we going to take?
Nice to meet you. Let's go.
It's totally working on
What is your deadline?
It was 7, but I consider 8 is my number.
I love it. I love it.
But really, great presentation.
Yeah, they're all. Yeah, this is good.
Thank you, Dr. Hoang. I really appreciate your support.
The code.
The code, yeah.
Also, I have an answer to your question.
Oh, yeah.
There's well, you were asking about the difference from energy curves, and there's parallel and perpendicular curves. So one of them has a perpendicular so like that's how it works. So it was in my previous I was like, it's just so It's like it's just like how and an entry point like jumps like sideways or goes up the same. It's a type of transition. So I had it written and I had it all laid out, and then I couldn't get it to work the way I wanted it to. Yeah, well, I never got started. I started trying to create something which is like a dye, but I wanted to like show like the reaction between that and so it's like a dye that dies like antibody. It's just I was trying to love it, and it's just way too complicated. So I took a step back and do a secondary.
What is it trying to reach?
Yeah, I mean, yeah, it went to my first. Well, but it wasn't like a bad. Well, I'll see you next semester.